Welcome, everyone, and I am so pleased to see how many of you are here today. It's wonderful to have so many people here, and I know that there are some people online as well, so we welcome them. So, introduce myself first. I'm Sandra Bressler, and I am the principal of the college until June 30th. That's okay. June 30th, it's fine. It's been a very rewarding time, which we'll talk about. We have a busy agenda today, so we'd like to get started. We have 3 parts to this meeting. We have the business meeting, we have an awards ceremony, and then a guest speaker. So first, we begin. The first slide. Okay. We begin by acknowledging that UBC Point Grey are located on the traditional, ancestral, and unceded territory of the Musqueam, Squamish, Tsleil-Waututh, and Syilx Okanagan nations and their people. Next slide. Every year I look forward to this event because it's a chance to pause and reflect on the remarkable accomplishments that we've made while looking forward to a fresh year ahead. I hope that while you are here, you'll have time to talk to your peers and enjoy the company of other members. As we know, and I really believe this, the membership is really the heart and soul of the college. And as this is a hybrid event, as I mentioned before, there are online guests who are here with us today, and also in the Okanagan. And if any of you have any technical issues, please put them in the chat, and we'll do our best to help you out. I am now going to ask those of you that can stand to please stand as we take a moment of silence for the friends and colleagues we have lost in 2025, 2026. Thank you. The college has many achievements to celebrate in the 2025-26 academic year. Next slide. We have 106, it says 103 on the chart, but we've increased it by 3, which is great. It's both. Oh, thank you. Okay, thank you. So we have 106 new Emeriti acknowledged by Vancouver and the Okanagan Senate. I'd like them to mention the names of our 3 new Senate convocation members. They are Lawrence Burr, Ruth Berkson, and David Wilkinson. We also celebrate the Order of BC recipient, who is Ruth Greneau from Pediatrics, and the Order of Canada recipient, who is Allison Audrey Eddy, also from Pediatrics. Okay. In 2025-26, we were even more active than last year. And if you look at the slide, you can see we've had 229 events and activities, of which 89 were organized by Harry Hubble of the Sports Special Interest Groups. So congratulations to him. And is he here? Well, please stand. Please stand. That's a wonderful. Thank you so much. Good, good. We will share the details of our events also in our annual report, which will come out in September. So what else did we do in 2025-26? We created a strategic plan for the next 2 to 3 years, and more will follow in the fall of 2026. We had the pleasure of the executive meeting with UBC deans in January, and Leslie Cormack, the principal and deputy vice chancellor of UBC's Okanagan campus in April, to discuss how we can work together and how the Emeritus College can benefit UBC on both campuses and vice versa. Now, on Giving Day in April the 8th, which I hope you all remembered that date, $43,647 was raised. My deepest thanks to our donors for their support and the development committee for all their efforts to raise funds. We reached 58% of our target for this year. So I'd like to add that we'd like you to consider supporting this special community so that it can continue to deliver the programs, such as this meeting and other activities important to the membership. We also organized new membership enrichment initiative, as mentioned on the slide. We always start with, so as I'm sure many of you know, budget changes dominated regular meetings that Wendy, the vice principal, and I had with Deputy Provost Janice Stewart. But we will talk, so that did, as you know, occupy a fair amount of time. But we also have been able to talk to her about other initiatives, and she has been very supportive of all that we've done. We co-sponsored with Faculty Relations 2 virtual retirement workshops for UBC faculty members, librarians, and academic program directors after the age of 55. I want to give thanks to the Transitions to Retirement Committee for all their hard work, and for Linda Leonard. Where is Linda Leonard? She is here. Thank you to her. You could stand too so everyone can see you. We subsidized 11 Emeriti from 9 departments for the $20,000 for scholarly activities. And a thank you to the Scholarly Subsidized Committee for adjudicating the applications. And is anyone here from that committee? Okay, why don't you take the stand? Another exciting event is that we signed a new memorandum with educational studies. And this is a big thanks to Joanne Archibald for leading the way in this. Now, of course, none of these events and activities could not have happened unless we have the dedication of volunteers and staff members. The slide. So you can see the slide here, how many people are involved in our college as volunteers. And a big thank you to all of you for your contributions. And now for the election results. Perfect. We welcome Wendy Hall, who is going to come up to the podium in a few minutes, from nursing as principal, and Paul Steinbach. Where is Paul? There he is, okay. From surgery as vice principal. And I will be assuming the role of past principal. I look forward to working with the new executive members next year. As Paul Steinbach's term as council member has not ended yet, an extra council position open up. So we have 4 new council members this year. The members at large with a 3-year term would be Nazir Jeddah from Pediatrics, Nancy Langton, and Don Wearing. Any of those? And I know that, and Catherine Backman from Occupational Science and Occupational Therapy will be taking on a 2-year position. And I know that Catherine isn't here. Are any of the other of you here? Just please stand. Anybody else? Okay. As we move towards 26-27 year, I would like to briefly reflect on my own experience. When I began my term as principal, we were in very challenging times. And not only challenging times for us, but, and I see that you're nodding, of course, very challenging time for the university as well. And we needed to provide what was called a balance-based budget, as all the other colleges were, and we were able to achieve this. So we are really proud that we were able to manage as we needed to manage in this very difficult financial time. So that was probably the biggest challenge, and that is now behind us because now we're looking to a new fiscal year where the budget for the college has been settled. This position has also been enormously rewarding to me. So much has been achieved, and I hope you could see that from all the slides that we presented. We have become a very, very busy college with many exciting opportunities that we've had, and there are more to come. I am very grateful to my fellow executive members, council, all volunteers and staff, because as you know, an organization is the sum of all parts, not only one. So they have been very helpful to making this past year the success it is. And I also would like to thank you, members who are here and those online and others who can't be with us for making this college a special community. So this is the end of my remarks, and to help us look forward, I'm going to turn the floor over to Wendy Hall. Oh, yes.
Excuse me, before we move on, as we welcome the new competition senators, I wonder if we should also perhaps thank the ones who are leaving and will have their last meeting tomorrow night. So we have John Gilbert, Paul Harrison, and Richard Spencer, who have given between 6 and 9 years of their time.
Thank you so much for reminding me. That was a terrible oversight. I should ask before we move on. Any other comments? Okay, Wendy, to you.
So I'm here to give thank yous, and I'd like to begin by thanking Sandra Bressler for ably leading the college through this year in what was a very difficult set of life circumstances for her. And we so appreciate your leadership. And I think we have an umbrella for you. Of course. Sarah will just run and get it for you. Thanks. And there you are. And thank you, Sandra. Also, I wanted to thank the outgoing council members at large. So Nancy Galini, who initially created and led the volunteerism group and contributed to the Scholars in Residence program. David Hill, who did a fabulous job of chairing our membership committee and moved the membership reps into new opportunities to meet with each other and talk and exchange ideas. and Sandra Wilkins, who did an incredible job on so many committees. She did a job on the Transitions to Retirement Committee, the Membership Committee, the Benefits Committee, and the Communications Committee, and she also helped to redesign 2 web portals. So that is an amazing contribution to the college. So please join me in thanking those members. And we cannot overlook Nicola Hall, no relation. And Nicola has dedicated 12 years to the Philosopher's Cafe, first at Tapestry and then at Seasons, and led 47 meetings over those 12 years with the Philosopher's Cafe. She's given an enormous amount of pleasure to the members of the residents at Tapestry and now Seasons, and to Emeritus members who joined her. So please come forward and get your umbrella, Nicola. Can you get down? I'll meet you partway. There you go. Thank you.
Thank you. And I hope you can find somebody else to take it.
We'll do our best, Nicola. And also, I would be very remiss if I did not thank Bill McCutcheon, who is leaving us now as the former principal of the college. He will still be with us in spirit and in many other respects, because I know he's very good about volunteering for things. And so thank you very much, Bill, for your very great service to the college. And Paul has the unenviable job, Paul Steinbuck, of working with me this year as the vice principal, so prepare yourself, Paul. Anyway, so I want to say it's my privilege to be taking on this role as principal of the college and looking forward to all the things we want to accomplish this year. As Sandra has said, the college has been remarkable this year and done a lot of really great things, and we want to continue that going forward. We've had conversations with Janice Stewart, who's been incredibly supportive of us, partly for helping us dodge a major financial bullet, which was the realization that the vice provost's office was probably going to come after our reserve funds to the tune of 95%, which would have left us with $4,000 in our residual funds that we had and $4,000 that we could have had as a slight surplus in our 2027 budget. And thanks to Janice, she very thoughtfully and kindly managed to convince the provost that this would not be a good plan for us to have happen. So thank you, Janice. And we are very grateful going forward. But as Sandra said, we did not raise all the money that we put in the budget that we were going to raise this year. We said we were going to raise $75,000. And we have to do this, because if we don't, we're going to have to start looking at ways that we can cut back. So I don't want to be the bearer of bad tidings, but the development committee, led very ably by Bob Armstrong, has done a massive amount of work to try and attract funding to the college. And I know there's probably a lot of people out there who think, a bunch of privileged university professors, why should we give to the Emeritus College? We have lots more important things to give to, and I get that. But I think the college has a very important role to play, and I think that we can help make retirement so much better for so many people that are leaving their positions on campus. So I'm hoping everybody thinks about that. So this year, we're planning to meet with AMS and GSS, the Graduate Student Society. We're going to look at whether we can set up some more memorandum of understanding like we did with the Department of Educational Studies. We're going to make more efforts to connect with the UBCO Emeriti, because they're a very important part of our organization. And it's easy sometimes to move forward with things in Vancouver and not be paying enough attention to what goes on in Kelowna. So we will make that a priority, and already plan to make another visit to UBCO and thank the members there for their contributions to the college. And we also will think more about what are some things we can do to make retirement even more exciting and pleasurable for the people who join the college. Because in my view, the college is an incubator for healthy aging. It shows what healthy aging can look like. People get involved, they get engaged, they're socially connected, there's support there, they get intellectual stimulation, and they can pay it forward to other groups of people by mentoring students and by mentoring new members of the academy. And that is what we would like to take forward for the future. So thank you very much for your time. And now I will introduce Patricia Shaw. Where are you, Patricia? Here she is. And Patricia very ably led the awards committee and told us that she had a very difficult time with the members of the committee adjudicating the awards because there were so many stellar candidates. So thank you, Patricia.
Thank you. Thank you so much. Hello, everyone. Is this on? Yes, it is. So as chair of this year's awards committee, I'd like, first of all, to thank my colleagues on the committee, Diana Larry, who is here today, and Professor Emerita of History, and John Hepburn, Dean Emeritus of Science. Is John here? No, I thank him. What a great committee. And their work was extremely dedicated and deeply collegial. It's a wonderful committee to have the honor of serving on. As well, we are very appreciative of the invaluable help of the Emeritus College administrative team. So Sandra Van Ark, Queenie Law, Sarah Close Hamayun, and Heather Calder for their consistently excellent support. I must also say that I am very honored to serve in this capacity as adjudicating the 2 awards that are sponsored by the Emeritus College is an extraordinarily interesting, inspiring, and humbling opportunity. The 2 awards are the Emeritus College President's Award for Distinguished Service and the Emeritus College Award for Excellence in Innovative and Creative Endeavours. There was, as was just mentioned, an impressive number of very worthy candidates nominated for each of these 2 award categories this year. Our committee is deeply indebted to the nominators of each candidate and to all those who submitted letters of support for the warm spirit of respect for scholarly excellence, collegiality, community service, and commitment to local, national, and global issues impacting societal well-being. I really appreciate all the effort that has gone into this. So it is my great honor at this point to invite Dr. Benoit Anton Bacon, the President and Vice Chancellor of the University of British Columbia, to present the first award, the Emeritus College President's Award for Distinguished Service.
Thank you, Patricia. Thank you very much. Well, thank you very much, Patricia, for the kind introduction and for your leadership of the awards committee. This is hard work, I know from experience. It's great to see everybody, and we have a beautiful day for it. I didn't know I would assist to the changing of the guards here. So let me start by thanking and congratulating you, Sandra, the outgoing principal, and your leadership team, and welcoming you, Wendy, incoming principal, and your leadership team. Thank you. Thank you for your service. Very much the same for incoming senators. Looking forward to seeing you at Senate next fall. Outgoing senators, we have one more day of work. I'm looking at you, Paul. You'll be there? Tomorrow. Everybody, it is my great pleasure and privilege to be here and to present the 2026 President's Award for Distinguished Service by UBC Emeriti. This is a well-known award. It recognizes those Emeriti whose volunteer community services has gone above and beyond. And we were just talking before about the quality and the number of nominations. above and beyond, and whose contributions post-retirement continue to reflect the very best of UBC's values. And today, it's my great honor to recognize an individual whose decades of service at UBC are marked by exceptional scholarship and public service, and whose outstanding contributions since his retirement continue to exemplify the spirit of this award. Everyone, I give you this year's winner, Dr. R. Kenneth "Ken" Carty. It's a great honor. Can you take a picture with me? Yeah. Take you back here. Yeah, let's do this here. Good? You're good? Now I'll say some nice things about you, Ken, to embarrass you before ceding the floor to you. Everyone, Dr. Carty retired from the Department of Political Science in 2010, and we're recognizing him today for his outstanding service to the UBC Faculty Pension Plan, of which I am a member. Thank you for your service. And it was a good year, eh? It was a good year. Where he served as trustee for the past 13 years, including 5 years as chair. That's a heavy lift. Thank you for that, Ken. In this role, he's provided thoughtful and steady leadership, helping guide the plan through complex governance and regulatory challenges. Pension plans are complicated? More every day. While prioritizing the best interest of its members. In doing so, he's helped to maintain the stability of a plan that thousands of faculty members and retirees depend on, reinforcing the trust so many place in it. Beyond UBC, Dr. Carty continues to contribute significantly to public life. I was interested to learn that he served on both federal and provincial electoral boundaries commissions over several decades, helping shape fair and representative electoral systems, mostly free of gerrymandering. I'm completely free of gerrymandering. Great. Work that demands great integrity, deep expertise, and public trust. He's also an active scholar and public intellectual who contributes to national and international discussions on democratic institutions, reflecting his ongoing engagement with the pressing civic questions of our time. Dr. Carty, for your remarkable contributions to UBC and our society, for your enduring commitment to service beyond retirement, it's my great honor to present you with the 2026 President's Award for Distinguished Service by UBC Emeriti. Please, everyone, join me in giving Dr. Carty a well-deserved round of applause. Thank you again, Ken, for everything that you do for UBC. It's a great pleasure to honor you today. I think Paul wants a few more pictures with us, and then I'll cede the floor over to you.
I've been invited to join in the
Yes.
Everybody step over just a little bit so we don't get out there. But that's great. You know what? Yeah, that's perfect. Great. Perfect. Yeah. Awesome. Here we go. And horizontal. Right there. Great.
Thank you again.
Over to you.
Mr. President, members of the Emeritus College and friends, let me just take a minute to thank you very much for this award. I think when you're recognized by your own colleagues, it's the sort of best award you can possibly win. And I'm genuinely and deeply grateful for it. About half a century ago, actually more than half a century ago, Elaine and I got a call to come out to Vancouver for a year or two to UBC. And we thought, well, we'll try it. We'll go way out there. But probably in a year or so, we'll find our way back east. Well, yet we're here, still here. Because if we came for a job, we found a community full of amazing individuals who quickly became mentors and colleagues and friends. And it was this community that we found and became part of that provided the basis for the opportunities that have allowed us to make a rather diverse and rich set of contributions, both to the university, but also to the wider provincial and national and international institutions that the university is so well placed to serve. I've been enormously grateful for all the opportunities I've been given as a UBC faculty member. I want especially to recognize and thank the support and encouragement I've had from my colleagues in what is frankly and honestly the country's best Department of Political Science. At UBC Press, where I served for 2 decades, and in the past decade at the Faculty Pension Plan with, again, another set of remarkable colleagues. Most importantly, I want to thank Elaine, who has put up with and even encouraged my meandering activities. I couldn't have done it without her. So thank you, thank Elaine, and thank you all.
Thank you very much, Ken. Thank you, President Benoit. Okay. So the second award category is the UBC Emeritus College Award for Excellence in Innovative and Creative Endeavours. And choosing amongst the several worthy candidates in this category was extremely challenging, as was the first. But in this case, what our committee finally decided on was to split the award between 2 candidates. And so we're very honored to have 2 candidates for this, the first of which is Dr. Carl Walters, Professor Emeritus of Fisheries. And my understanding is that Dr. Walters isn't able to be with us today, but it gives me great pleasure to honor him as the co-recipient of the UBC Emeritus College Award for Excellence in Innovative and Creative Endeavours. It recognizes UBC Emeriti who have demonstrated excellence in their engagement in innovative research, artistic creation, or new applications of previous research since achieving emeritus status. It also allows us to celebrate and honor emeriti who have consistently demonstrated outstanding achievements beyond their scholarly work. The following excerpts from Dr. Walters' nomination materials speak compellingly to his exceptional achievements. And these are quotes. Carl J. Walters is one of the world's most influential fisheries scientists. The next quote, a defining feature of Walters' career, and especially his post-retirement years, is his commitment to using science in the service of communities and resource users. The next quote, his concepts of adaptive management and foraging arena theory are fundamental to the discipline. And as a co-creator of the world's foremost natural resources modeling software suite, which is called EcoPath with EcoSim, abbreviated EWE, he has had a transformational impact on our understanding of the ecosystem impacts of fisheries. Very relevant in our world today. The next quote, the U.S. Department of Commerce's National Oceanic and Atmospheric Administration, NOAA, called EWE, EWE, one of the, quote, top 10 scientific breakthroughs of the last 200 years. And finally, the list of 116 journal papers since retiring in 2013 clearly shows that retirement was only a change in scenery and salary. So please join me in warmly congratulating Dr. Walters on this achievement. And the second recipient of the Emeritus College Award for Excellence in Innovative and Creative Endeavors is Dr. David Lay, who I'm very pleased to say is amongst us today. Welcome. Thank you for being here, and thank you for your tremendous achievements. This award recognizes, as you have heard, UBC Emeriti who've demonstrated excellence and engagement in innovative research. The following excerpts from your nomination materials speak eloquently to your achievements. First, since his retirement from the UBC Department of Geography in 2018, Professor Emeritus David Lay has continued to redefine the social geography of global cities through a second act of profound scholarly and civic significance. His 2023 landmark volume, Housing Booms in Gateway Cities, has been recognized as a, quote, definitive comparative study of housing market bubbles, not only in Vancouver, but across the world, also in Hong Kong, Singapore, Sydney, and London, and has garnered international praise as timely and groundbreaking, meticulously researched, and a stellar contribution. Dr. Lay has also emerged as a vital public intellectual through hundreds of media interviews and pro bono expert insights. He has translated complex scientific and judicial data into accessible public discourse, fundamentally shaping housing policy and affordability debates. We all know how relevant this is to our lives here, but also globally. Next, Lay's post-retirement research is not simply additive, it's genuinely cumulative, intergenerational, and prophetic. And finally, his work exemplifies the spirit of the UBC Emeritus College by combining world-class academic rigor with courageous, real-world community impact. Please join me in congratulating Dr. Lay. Oh, it's my pleasure, my honor, indeed. Do you want to present? Yes.
And we'd have to take pictures.
Yes.
That's the other part of this. That's correct. With you. Come forward.
You don't sound very retired to me, so.
Okay, thank you very much.
I very much appreciated Ken Carty's comments earlier because, as he pointed out to me when we met in the next room, we have a common intellectual ancestry, which is Jesus College, Oxford. I went there primarily as a geographer to play sport. He went there, I think, to do more serious things. I arrived here in 1972, very, very young and very, very hairy. I arrived in a department that was quite a conservative department, a very good department, but a conservative department. And I could have been a difficult person to absorb. But I was... And in hindsight, I am more and more impressed by the way in which difference was treated as an asset. And I think that's something we can learn about continually. difference, of course, in lifestyle, but also difference in perspectives. And if I have one reflection on the university since my retirement, is that it is becoming increasingly difficult to maintain that welcoming of difference in perspective, while we, I think, are getting A+ marks in terms of welcoming other forms of diversity. I'm very, very thankful for this award. I started in 1972. I concluded at the end of 2017. So this is my only show. For a geographer, I've been much too sedentary, some would say. But I joined a very good department, which in fact continually became more and more interesting as the years unfolded. This is a real capstone achievement for me to be awarded this. I hold in very high regard my peers, you, of course, and other emeriti who are not here today. And I know that many, perhaps most of you, could easily be standing here today in my place. So this means a lot. I think that events like this also prove the immense value of the Emeritus College in not just recognizing, that of course is important, but also marshalling the human capital beyond retirement that is reflected in this room, the tremendous expertise which through the college is an acknowledgement of that expertise, and I think also a facilitator of it continuing to flourish and prosper the university. I know many of us continue on university committees. We do our research, and I think to acknowledge that enables UBC to be advanced as well. So thank you very much. Thank you, Patricia. Thank you for your committee. Thank you for my nominees, who I see here. Thank you both very much indeed. And I hope you didn't tell too many lies in your letter. Thank you.
Thank you very much. Congratulations. Thanks, Patricia. Thank you very much for those beautiful words and inspiring words. And the commentary that both of our speakers have given about how invaluable our experiences are within the Emeritus College and appreciative we are of the college's support throughout these years is greatly appreciated. So great. So please, before we break, join me in congratulating our award winners one more time.
Everyone, it gives me just great pleasure today to introduce our speaker, Dr. Jess McIver. Dr. McIver joined our department in 2019. That is when we advertised, had an open competition. Usually we target certain disciplines in the department, but we had an open competition. 600 people applied. Jess won the competition, and we were very, very fortunate, very lucky. Jess did her undergraduate in Syracuse University and her graduate work in University of Massachusetts in Amherst. And during this time, work was going on. You know, people have been interested in gravitational waves, gravitational wave detections for decades, for a long, long time. I think it was 1916 that Einstein's work on general relativity indicated that there would be gravitational waves. And so people have been working on this for a long time. Jess was fortunate to go to 2 universities that had programs connected with gravitational waves and gravitational wave physics. And so she was in her second year of her postdoc when the first detection happened. Is that correct? And so she was well poised, grounded, I think, in gravitational wave physics to join the collaborations, the LIGO collaboration that was going on in the States. And so she's going to tell us about that today. This is extremely difficult physics. The detection methods, detecting movements down to many orders of magnitude shorter than a nanometer, and guarding against having false detections from footsteps and tides from many miles away. So Jess has experienced all this, and she's been working from our department in gravitational wave physics, and I'm really excited that she's going to tell us about it today. Jess.
Thank you so much for having me today. We're going to attempt to take you to space. We're going to see about turning the lights down a little bit. So I want to take the temperature of the room here. We're running a little bit oh, thank you so much. That's perfect. We're running a little bit over time. Are people happy to hear about space? Yes. Okay, let's do it. We're going to go to space. So up until maybe the past 3 or so decades, everything that we learned about the universe, we learned with light. So we learned about the way the universe is expanding. We learned about dark matter, dark energy, these forces that are shaping and acting on our universe that are very difficult to see, to detect. But we had, through many generations, especially of technological development, evolved new ways of observing the universe with light. And as our technology improved, we were able to get a new glimpse into phenomena that have entranced humans for many millennia. So here we're looking at the Northern Lights. This is a time lapse from the International Space Station. And as our attention has turned to the stars, so we've been able to build new technologies. So you're seeing here an image taken by the Hubble Space Telescope. This is matter that's been blasted away from the middle and outer layers of a star in a supernova explosion that's traveling thousands of kilometers per second. And we're seeing here, this was a supernova that was so bright in the sky a couple millennia ago that it was actually visible in the daylight. And at the heart of this explosion is a zombie star, a dead star that's the old core of this previous massive star. These are called neutron stars, and they're so dense that even a tablespoon of the matter of the star would weigh more than a mountain. The most extremely dense matter in the known universe. We've even, from the Earth, been able to expand our view of galaxies like our own. So this is an image taken by the Keck telescope. They've used some very advanced adaptive optics. You can see the lasers pointing up into the sky to try to measure these tiny perturbations in the atmosphere and correct for these to get an ultra-sharp image that we've been able to use to study distant stars and distant galaxies. We've even been able to use light to learn about gravity. So our current best understanding of the true nature of gravity is Einstein's general relativity. So we've got a complex tensor equation here. So all we need to understand is that matter, this distribution of matter and energy in the universe, is going to inform the curvature of space-time, and that curvature is going to inform the movement of matter. So gravity, as we experience it, dropping apples from trees in the orbit of the moon around the Earth, this is the nature of objects following this warped curvature of space-time. And as we'll see, if you introduce some perturbation into this stretched fabric of space-time, it's going to ripple. Like tossing a coin into a pond, we're going to see that these ripples in space-time are gravitational waves. So how do we know this is true? So why do we believe that general relativity is the right description of gravity versus Newtonian mechanics? There are a lot of signs that we can look for. So if it really is space-time being bent, it should also bend light. So this is another element that light has allowed us to investigate. So this is the nature of gravity. And a fairly simple experiment that you can do is look for some very massive object, like a star. You introduce this between you and a distant source of light, like a distant star or a distant galaxy, and you watch to see if the position of that star galaxy is going to be changed. So the trick is that the sun is also bright, so you also need something to shield the sun's light, so you really need to do this during a total eclipse. And this measurement was actually made only less than a decade after this prediction by Einstein, as Bill mentioned, but over 100 years ago now, so 1919. This was the famous Eddington experiment, a total solar eclipse confirmed lights all askew in the heavens. And they had measured this deviation of the position of the star, bent and warped as it passed by our sun. It's worth noting this was confirmed just a few years later by a Canadian-led team. We have also now, with the advent of improved telescopes, been able to observe the presence of black holes with light. So here's an artist's illustration of a black hole with a companion star. And if you have a telescope with good enough resolution, you'll be able to resolve the position of the star and also the glowing of the accretion disk around the black hole as it's swallowing and pulling off the outer layers of its companion star. So with the two of them together, looking at how they're orbiting each other, you can even measure the mass of those black holes and their companion stars. So with light, we have been able to get some data about these dead stars, these stellar remnant black holes. And we do expect to see these as part of the natural evolution of very heavy stars. So what you're seeing here in the top, so these are for stars like our sun, so less massive stars that will form from a smaller clump of dense gas and dust. They will evolve over time. They will expand. This is appropriate music. The glory and the majesty of stellar evolution. They will expand, become giants, and then very, very slowly they're going to cast off their outer layers and make these beautiful planetary nebulae before finally the core, the husk of the star is going to cool over many, many, many millennia as a white dwarf. And the rarer case, so these are more massive stars that form from larger clumps of gas and dust that are going to they'll evolve much more quickly into these supergiants, and their fate is to explode. And you may remember this image from a few slides ago. So this is the Crab Nebula, the remnant of a supernova explosion fairly close to us in our galaxy. And if the star is something like 8 to 20 times the mass of our sun, the core of that star will become a neutron star, as we saw before, the most extreme matter in the universe. But if it's bigger, if it's even rarer, if it's more massive than about 20 times the mass of our sun, it will collapse. It won't be able to support itself against gravity, and it will collapse to a black hole. So this black hole, this warping of space-time that's so infinite that not even light, once it passes this event horizon, can escape. And it's not just dead stars that we think form black holes. We also have another class of black holes that are lurking in the heart of nearly every galaxy that we've observed, including spiral galaxies like our own, and like M87, as you see pictured here. So within the sparkling stars and the gas that's becoming a nursery for new stars, at the heart of these galaxies are these monstrously massive, supermassive black holes that can be millions or billions of times the mass of our sun. And how do we know these are here? So you may have seen this image in the news. So this is the first ever image of the shadow of a black hole. You can see light bending around this black hole from glowing gas and dust. So this was taken by the Event Horizon Telescope of the black hole in this galaxy M87. So this is a radio telescope, and what they do is they can use radio telescopes all over the Earth to make roughly an Earth-sized telescope that has the resolution needed to probe into these regions of space. So there are only about a handful of supermassive black holes that we expect to be able to image this way, but it's an incredible window into the nature and the reality of black holes. We also see evidence in very distant galaxies. So there is a galaxy here in this image. Does anybody want to guess where it is? Where are we thinking? If you're thinking that little dot in the middle, you are right. So here we have a galaxy, and we have something that's, again, monstrously energetic, that is forming these gigantic plumes that are many, many times greater in volume than the galaxy itself, with all of its billions of stars contained within that galaxy. So what's driving this? What's producing this enormous amount of energy that's pushing this interstellar gas and dust together and causing it to glow? Well, we think that these engines are the supermassive black holes. So this is a nice simulation produced by NASA that shows this dusty accretion disk that's at the heart of it, showing us, aligned with the spin of the supermassive black hole, this warped magnetic field that we think can drive these huge currents of energy out into deep space and form what we call these lobes, these very, very large features. So we have a lot of evidence that supermassive black holes exist. We can also see with our telescopes these evidence for dead stars, but we don't yet have any evidence for anything in between. So nobody has observed yet what's called this intermediate mass black hole between roughly about 100 times the mass of our sun and the millions to billions that are these supermassive black holes. So something that's really interesting for astronomers is to try to understand what is the impact of these dead stars on their environment. How do supermassive black holes form? What is this telling us about stellar evolution, the way that stars live and die, and what does this mean for us in terms of how we evolved to be here in this part of our galaxy and in this part of our solar system? So what you're seeing here in this simulation is an animation that's sped up many, many times, and if you can squint, you can see in the background this evidence of something dark that's causing the light to bend around it as it moves. So here, for these intermediate mass black holes, and then also for the stellar mass black holes that don't have a companion star to make an accretion disk that we can see with a telescope, we're going to need to do something different. We're going to need something else, something that's beyond light in terms of sensing these. So this brings us to gravitational waves. So these are tiny ripples in the fabric of space-time itself, and they propagate at the speed of light, and they're very, very weakly interacting. So I deeply admire my colleagues in the very difficult job that they have to try to account for gas and dust and all the things that light can encounter on its journey here to Earth. We don't need to worry about any of this. So the gravitational waves, they're going to propagate right through the Earth. They'll go through billions of light years. They'll go right through galaxies. We don't need to account for that interaction if we are ambitious enough to build something that can detect these. So they're extremely tiny warps in space itself as they're passing through us, even now. So let's try to understand this. So gravitational waves, what does that mean? So you may be familiar with waves in other media. It's probably one of the most famous examples is water. So waves being just this transfer of energy through some medium. But it doesn't have to be water. It can also be more unusual phenomena. So waves can appear at many other places in nature. So this is one of my favorite examples. This is a time lapse, and you're looking at clouds now. So these are layers in the atmosphere, thermal layers, and these clouds that are beating up against the shore of this mountain. So waves appear many places in nature, including in space-time. So this is the canonical source of gravitational waves. Here we've got two dead stars that are orbiting each other. So what's happening here is they're emitting energy in the form of gravitational waves. So this is propagating away. And what that's going to do is it's going to drive those two dead stars together. Whether they're neutron stars or black holes, once they start getting close together, they're emitting an appreciable amount of energy in gravitational waves. And this is going to drive them to collide. So how can we understand this? I promise this is the only equation I'm going to show you. But there's a lot of really cool physics here. So we've got something that's moving in space. So in order to generate a gravitational wave, we need some asymmetry, some kind of asymmetric acceleration. And again, that could be as simple as two dead stars that are in orbit around each other. And what this equation is telling us is that the strength of this wave over time, so you can actually completely derive the dynamics of the system that's generating these waves. So the strength of the wave over time, so this is proportional to, you may remember if you've done physics, big G is a very small number. And then you may remember C is the speed of light, a very big number. So we've got a very small number divided by a very big number to the power of 4. So already whatever else is happening on the other side of this equation, this effect is small. This is our intuition that this is a very, very tiny effect. And then the next term that we see, so this is telling us that the strength of the wave over time, this is going to follow the dynamics of the system. So this is following this asymmetric acceleration. This is the second time derivative of the quadrupole moment, but that's what that means. This asymmetric acceleration. And then I would argue the most important elements for astronomers. So in astronomy, finding the distance reliably is extremely difficult to do with light. You have many features that you're trying to calibrate against each other. You have a lot that can interfere with the path of the light. But here, we've got this signal amplitude, and it's directly proportional to 1 over the distance. So it's actually fairly straightforward to infer distances with gravitational waves if you have a good model, which, as it happens, since our signal does not have any interactions, on its journey to us, we have functionally perfect models in the world of astronomy. So we've got this thing in space. It's doing whatever it's doing. Maybe it's orbiting around. This is generating a gravitational wave signal in time. So that could look something like this time series. So it's going up and down as it's passing through space. If this wave is passing into or out of the screen, or maybe for people looking this way, into or out of this screen, what it's going to do is it's going to stretch and squeeze space-time. So I'm going to do an interpretive dance for you. So yes, stretching and squeezing space-time in 2 orthogonal directions. This is the effect that we expect gravitational waves to have as they're passing through us and through our detectors. So this motivates the shape of our detectors. So in order to sense these, we want to be able to test changes in relative distance, so distance in 2 perpendicular directions. And this is how we design our gravitational wave detectors. So these are 2 orthogonal arms. We're going to use laser light, coherent laser light. We're going to split it up into 2 parts, and we're going to use those essentially as a timing system to time how long it takes the light to make the journey. Something else that you might notice if you're looking at these dots wobbling around, if you compare 2 dots that are close together, you'll see a smaller effect. If you compare 2 dots that are farther apart, you're going to see a much, much bigger effect. So this is motivating us to build big detectors. So these are massive. They're on the scale of kilometers. Let's get a little bit more intuition for how this works. So we're going to take a tour of this Michelson interferometer that we'll use to detect gravitational waves. So here we've got an incoming gravitational wave, which allows us to see our signal over time. And let's break this down a little bit more. So we've got this coherent laser light split up into 2 orthogonal directions. It's going to travel, in our case, for 4 kilometers before bouncing off a mirror and then returning to the beam splitter. And if we have no relative change in distance between those 2 arms of the detector, we see nothing. However, if you introduce a gravitational wave into the plane of the detector, you start to introduce this relative change in length of the arms, and we can actually sense this as a relative difference in phase of the light. So we're actually able to measure this change in amplitude over time. We get the full dynamical signature of the source that generated this gravitational wave. And I want to show you what these look like in practice. So we're going to take a drone ride. We're going to go up to see, this is Lago in the swamp in Livingston, Louisiana. So we're looking back towards the laser and the beam splitter and the photodiode readouts, only about 2 kilometers. So we're hovering over the mid station. And here again, we're showing you probably roughly only about 1/3 of the size of the arms. So if you're in the market for building a gravitational wave detector, I do strongly recommend not putting it in the swamp. Something else that you might notice is the trees or the lack thereof. So keep this in the back of your mind. If we've got some time to talk about the realities and practicalities of how hard this is to do, we will come back to those trees. But let's get a sense of what's actually in here. So here's the installation of the equipment that's currently inside the vacuum for the 2 LIGO detectors. This is the Laser Interferometer Gravitational Wave Observatory. So this is what's holding on to one of those mirrors is at the bottom here, and that's going to get lowered down on top of this seismic isolation. And then we'll see one more, which is just the final checks of the mirrors. This gives us a pretty good view of the coatings. So one of the problems that we have in terms of noise is the motion of the molecules on the surface of the optics move enough to introduce a relative distance change that we can measure. And the Quantum Matter Institute here at UBC is working really hard on finding materials that have enough reflectivity for our laser lights, but are much quieter in terms of how much they wiggle around. This is our thermal noise problem. So all in all, what does all this engineering buy us? So here's a simulation of our real 2-scale ability to sense relative distance. So we're looking at the hydrogen atom. We started out zooming around with the electron, and we're going to zoom in now to the surface of the proton. So this is our real 2-scale ability to sense this relative displacement. It's about 10,000 times smaller than the diameter of a proton. So one of the most sensitive measurements that humanity's made to date. And we actually have 3 of these detectors with comparable sensitivity in operation. This is important because unlike a telescope, where you're pointing the telescope in the sky and you know roughly where in the sky you're pointing, or ideally exactly where in the sky you're pointing, so gravitational wave detectors are much more like microphones. So they're sensitive to the whole sky. So if you want to be able to pinpoint where in the sky a signal is coming from, you're going to need 3. 2 will get you a ring. 3 will get you a point in the sky if you're clever about your sensitivity as a function of space. So we actually really rely on our sister detector, Virgo, which is a 3-kilometer detector near Pisa in Italy. And it's worth mentioning also there's another 3-kilometer detector underground near the Kamiokanda mountain in Japan, that's called Kagra, and an additional 4-kilometer long detector called Lago India that will be placed right in the middle of India. So let's put this all together. Let's see a full picture. So here we've got 2 dead stars orbiting around each other. They merge, and this whole dynamical signature is emitted at the speed of light as a gravitational wave. And it's going to travel potentially for billions and billions of years before it reaches the Earth. And as it does, as it travels through space, it's going to introduce this stretching and squeezing. I'm going to warn you that this is dramatically exaggerated for reasons that will become apparent shortly. We call this the Jello Earth. Look at it go. So we've got the stretching and squeezing. And as that signal passes through our detector, So it's going to introduce this relative change in length in the arm of our detectors. And we're going to be able to measure exactly what that signal is through the change in phase of the light. So you're all experts now. So I'm going to show you what we would see if you could build a perfect telescope. What would you see if you could look at the sky and find a LIGO source? So you might see something like these two roughly 30 solar mass black holes. They're orbiting around each other, they're radiating gravitational waves, and eventually they're going to merge. And that final black hole is going to ring down like a bell, which you can see in the wobbling of the sky and the stars in the background. Now let's take a look at that same source through the lens of space-time. So here now the colors are showing us the curvature of space-time, and the bottom trace that you see here. So this is showing us this change in amplitude over time that's generated by this source, this two black holes. So general relativity tells us that as these two black holes get closer and closer together, so the signal is going to go up in frequency, which gives it this famous name of a chirp, like a bird. It's going to go whoop. And it's also going to become much stronger in amplitude. So strong that as these two black holes approach their merger, in about 1/10 of a second, the system is going to radiate about 3 solar masses of energy in the blink of an eye. So in sheer power, in sheer luminosity, it's going to outshine the entire visible universe for that moment that it merges. And then again here we've got this final black hole that's going to what we call ring down after the merger, and that whole signature, again, propagates away towards our detectors at the speed of light. Now, what I'd like to do is play you some real data. So this is data from the very first detection of gravitational waves that we just celebrated the 10th anniversary in the fall. And this data is shifted a little bit to make it easier to hear, but you will hear, if all goes according to plan, you will hear this whoop, this chirp in the data. So let's give it a try. Anybody hearing a chirp? It's a little bit soft, but if you like to come hear it properly, we couldn't link this up to the speakers. Please come down after the talk, and I'm happy to play it again for you. But you might be wondering, so I was saying roughly 30 times the mass of our sun. How do we know that? How do we know what this thing was, what the masses were of the two black holes that collided? So I will show you an approximation of how we do our data analysis. So what we're going to do, so we're trying to fit our noisy data that's in blue, and we're going to use our model that's in gold. And we're going to evolve the masses of our model until we've got a good fit in phase. And once we've got that fit, remember again, the strength of our signal just goes as 1 over the distance. So we can simply scale our data because general relativity tells us how strong that signal should have been at the source. So let's take a look. So here we're evolving the model in mass. This is going to tell us the phase. Once we've got a good fit for the phase, we're simply going to scale it to get a measurement of the distance. And again, just to underscore, this is an extremely powerful tool in astronomy to differentiate distance, totally independently of cosmic scalings that you would use for light. And our next most famous, arguably, our next most famous signal came only about a year later. So this is the merger not of two black holes, but of two neutron stars. And you might notice that the time scale here is much, much longer. So these lighter objects, so they're only about 1.4 times the mass of our sun, they're going to whiz around each other thousands and thousands of times in the sensitive frequency range of the detectors. So here again, I'm going to try to play you some data. This is simulated this time, so it should be a little bit easier to hear. There we go, the sounds of space-time. But this is a particularly famous event because it had a counterpart. This is the first multi-messenger discovery with gravitational waves and light. So what we're looking at here is a sky map. The blue choices that you're seeing, so these are the sky maps that come from gamma ray satellites. So this is a powerful event that emitted all across the electromagnetic spectrum in addition to gravitational waves. And this double banana that you see in green, so this is what you get with two detectors. This is the best we can do with 2 detectors for a source that's quite nearby. When you add the third, so this is with the 2 LIGO detectors in Virgo, now you get a point in the sky, or an area. But remember, we also get distance, so we're really seeing a volume, a possible volume populated with galaxies, which is what our partner astronomers use to identify the host galaxy for this source. So you're seeing here, this is NGC 4993. And these events carry a lot in their light signature in addition to gravitational waves. So here you're seeing 2 images. So these are 4 days apart, and this is the electromagnetic counterpart. You'll notice it's getting dimmer, and it's also getting redder. And this is telling us about the signature of radioactive decay and the production of heavy elements from this merger of 2 neutron stars. So let's see a simulation of all of this together. So here we've got these neutron stars. They're orbiting around each other. They're emitting gravitational waves, which is drawing them closer together. They're going to become close enough together to start to tear each other apart tidally. And as they merge, they're going to release this burst of gamma rays, highly energetic burst of gamma rays, and the sea of neutrons, highly dense neutrons. So this is a very rare environment in the universe because it only takes a neutron about 12 minutes to decay. You really need a huge density of neutrons in order to pile up enough to make elements like gold and platinum. So if you're wearing any gold or platinum today, think a neutron star. This is very likely a distant cosmic collision. So where are we now in terms of what we've learned? So what you're seeing here, I'm just going to emphasize that the x-axis here, the horizontal axis, has no meaning other than it's just getting kind of hard to fit everything on one plot, which is a nice problem to have. The y-axis, the vertical axis, is mass, measured mass in solar masses. So here, each one of these pink and yellow dots, these are neutron stars in yellow and black holes in pink, with masses measured with light, with telescopes. And every blue dot that you see, in addition to the orange ones, so this is a dead star with a mass measured with gravitational waves. So what we're seeing here, these are all the results that we had from the end of our most recently finished observing run, that was observing run number 3. And then this is the same, but now with the data added from our most recent data release. So here we're seeing that gravitational waves is starting to absolutely dominate what we understand about dead stars. It's also revealing this population that we hadn't been able to access with telescopes. So black hole masses that are well above 20 times the mass of our sun, which were all we'd been able to observe with telescopes focused on those X-ray binaries, those black holes with partner stars and our galaxy. And I want to advertise, if you find this interesting, we're only about 2 weeks away from our next data release. So this number is going to go from about 300 to about 400 in just a couple of weeks. And each and every one of these points, again, is a fully dynamical signature. So we're able, for every single one of these detections, to infer the spins of the black holes, the masses, where they are in the sky. Are they isotropic? Do they follow the kind of distribution that we see for luminous matter? We're now, for the first time, getting insights into these really key questions that only gravitational waves can answer. And I want to tell you 3 of my personal favorites in terms of events that I think are the most interesting that we've found so far. So here is an event with quite a high mass for the final black hole, so roughly about 142 solar masses. You may remember before that we had said there were no previous measurements of black holes anywhere between about 100 times the mass of our sun and millions to billions, which is the supermassive black hole range. So arguably, depending on how you're counting, this is a first measurement just with its toe in that range of intermediate mass black holes, could be telling us something about how these supermassive black holes form. But more interestingly, we can also estimate the masses of the 2 black holes that merge. And one of them in particular is way bigger than we know how to explain. So this 85 solar mass black hole, we can't explain. It should have torn itself apart completely. We expect to have this gap from this production of matter and antimatter that can spontaneously inflate the star, and then as it compresses again, it should get hot enough to tear itself apart completely. So this is a really interesting clue, and one that could indicate that one or potentially both of these are black holes that formed from previous mergers. And this would indicate that there are regions of space that are so densely populated that it's possible to have multiple mergers within a Hubble time. So fast enough for this all to happen and then for the signal to make its way to us across billions of light years. So the next one that's very interesting, in my opinion, this is a neutron star and a black hole. So this simulation is showing us one of our most recently detected events. And what's unpredicted about this one is that the black hole mass is so small. We weren't expecting to see partner neutron stars and black holes where the black hole mass was comparable, so roughly 3 to 5 times the mass of our sun. It's small enough that the neutron star is actually going to get torn apart before it enters the event horizon, which means it could produce heavy elements like platinum and gold. So this is a totally different pathway than we had expected, and possibly another avenue for introducing these heavy elements into the universe. And then the last one, so this is actually on the front page of the Globe and Mail back in the fall. So this was one of our most recent discoveries. So from your perspective, the left, so this is the Nobel Prize winning very first detection. And then on the right here, this is a detection made almost down to the month, 10 years later. And as far as we can tell, these events are identical. They don't come from the same place in the sky, so they're different events, but they've got the same masses, the same spins, the same distance away. The only difference between these is the improvements that we've been able to make to our detectors. And this one was so clean, and more importantly, so boring, barely spinning, just canonical masses, that we were able to do these very novel tests of general relativity to the kind of precision that we haven't been able to achieve in any other way. So gravitational waves are unlocking a totally new understanding of fundamental physics, and that's only going to improve as the detectors themselves improve. So I want to do a quick time check. How are we doing, Bill? How are we feeling? Do we want to go a little more? You want to hear about trees? Oh, you're about to get some trees. Okay, let's carry on. So I do, this is what I spend much of my time thinking about, and what my group spends a lot of our research time devoted to is the realities of trying to make these measurements possible. So here's an aerial shot of LIGO Livingston. This is the one in the swamp in Louisiana. And we're going to take a little tour just to get a little bit more of a flavor for how complex this is. So if you end this simulation thinking, wow, that was really complicated, we've achieved our goal. But we're going to start zoomed out. So this is actually LIGO Hanford, which is in the desert. And we're going to zoom in and we're going to follow the path of the laser beam just to get a flavor for what's involved in all the different optical cavities that have to work together to make this measurement. So the vacuum chambers that you're seeing, they're quite large. They're maybe about 10 meters tall enough for a person to go stand in there and work very comfortably. And then here is the beam. So it starts at what's called the PSL. This is a pre-stabilized laser, not a pumpkin spice latte. And it's going to get steered into this 3 optic cavity in pink. This is called our input mode cleaner. We use it to tune the beam and we use it to clean the beam. And I'll maybe leave that there. And then it passes through this 3 optic cavity in this lime green color. What it will do is recycle the light that exits the beam splitter. But for now, it's going to go straight through to the beam splitter. And this is going to get split 50% in 2 directions, just like we saw in our simple schematic. So we're going to zoom all the way out, and I'm going to tell you about a new mirror that I didn't mention before. So we got 2 mirrors lining each one of those arms. This makes it what's called a Fabry-Perot cavity. And this is going to cycle the power in the arms up by a factor of about 300. And this is vitally important for us to reach the kind of sensitivity that we need. Now we're going to zoom all the way out to the end station, take a look at one of these mirrors in practice. So they weigh about 90 pounds. They're about yay big or so. And they're hung, if you squint, you may be able to see, they're hung from these very, very fine fibers that are also made of the same fused silica, which really helps us to push down that thermal noise as much as we can. All right, so the light, it's made its journey in the arms. It's going to come back and arrive back at the beam splitter. And once it does, 50% of that light is going to get recycled in this power recycling cavity we saw before. 50% of it's going to come to the signal recycling cavity, which serves a similar purpose. And then finally, it's going to get steered down to what we call a bow tie cavity, this 4-optic cavity here. And then that tiny little hemisphere that you see, that is our photodiode. And as we have a gravitational wave introduced into the plane of the detector, it's going to stretch and squeeze that space. and introduce a signal that's going to pass through what we call our signal optics, as you see here. So this is a little bit more detail into the journey of the light, which is going to give context to the trees. So here is, again, the simulation for this very, very first Nobel Prize winning detection. So something that I haven't mentioned, so I've been boasting about how our signal is able to pass through the Earth and gas and dust, and all of that is true. So we don't worry about the time of day, we don't worry about clouds or weather, but we do worry about ground motion. Because if you shake that ground too much, you need each one of those 12 independent optical cavities all to be resonant with light at the same time. And if you wiggle things around too much, then we're not able to take any data at all. So we want to be observing 100% of the time. And then ideally, in order to locate things in space, you want this green part of this bar to be 100%. So this is when all 3 detectors are taking data at the same time. So we only achieve roughly about 1/3 of the time right now. We want to be doing much better. So we have 1 detector at least operating almost 90% of the time. Just to give you a flavor for how hard this is. This is across the 3 detectors, 2 in the US and 1 in Italy. And this brings us to trees. So what you're seeing here on the bottom, so each one of these bars is a week. You want that week to be green because that means we've been taking data. If the week is not green, we try to understand why. So what's preventing us from taking data? Brown means that there's something going on in the environment. There are 2 regions that I want to talk about. One is related to those trees or the lack thereof, more importantly. The second, though, you'll notice this is time since the start of the run, so time since the end of May 2023. So we have a lot harder of a time as winter comes, and this happens every year to both detectors, all 3 detectors even. Does anybody want to take a guess at what our environmental challenges are? So getting on to about week 24 or so. We will get to the logging, absolutely. So the logging happily for us did stop at about week 12. It felt like eternity, but it did eventually end. Yes, it's strongly related to ocean weather. So this is late enough that hurricanes season has stopped, but they are storms, you're right. And it's the sloshing modes of the ocean bodies of the Pacific, the Gulf of Mexico, and the Atlantic that cause what we call microseismic noise. So it's the resonance of the oceans themselves that are excited. Every winter, we have a terrible, terrible time taking data, even with all of our advanced seismic isolation. But indeed, as you say, let's focus on that logging. So given what we've said in terms of the instrumentation of a gravitational wave detector, I would like you to imagine the worst possible place that you can think of for them to be logging. I will say the whole detector is surrounded by commercial logging. All right. Yes, so we have multiple places for mirrors to be, but the highest density of mirrors, I agree with you. That would be the worst possible place. And indeed, right, so this is next to our beam splitter, next to our laser, next to our photodiode readout, and they were out there about 20 meters away. And what would happen, you can see this in our ground motion trend. So this is this bottom trend here. So this is the start of the UTC day. Right about here is local 5 to 6 a.m. time, and this is when they'd clock in, and our ground motion would go whoop, just through the roof. They turn the trucks on, they're dragging trees, they're knocking trees down, they're dragging those trees elsewhere in the trucks. And you can see at almost exactly the same time, we lose light resonance. So the top trend is telling you about what the detector's trying to do. You always want it to be in the state up at the top bar. And then you can even see us valiantly, we're trying to get that lock back. We give up for most of the day. And then it's not until the loggers clock off that we're finally able to succeed and get data. So we lost about 1/3 of our time for all of those 12 weeks that they were logging. So yes, if you are in the market to build a gravitational wave detector, logging, you don't want that anywhere near your detector. And then I'd like to tell you just a couple more anecdotes that are close to my heart. This is what we call a glitch. So this is a transient noise excursion. You can see it on the left here. This is our real gravitational wave strain data, actually only a little while away from our very first Nobel Prize winning detection. And then on the right here, this is a similar time frequency plot showing you data from a nearby sensor, which is in this case a microphone. And we're staring at this with our human eyes, and we're saying, wow, look at you can see the articulation of different resonances. What could it mean? And the wonderful thing about the human brain is that if you give the brain a time series, it has no problem at all interpreting this. So I'm going to play you the sensor data, see if you can tell me what it is. Here comes the next one. So this was actually a telemarketer who's attempting to sell us something. So this was a fairly easy fix. So we went into the pre-stabilized laser enclosure and we turned that phone off. But there was some danger there for a while that you might obscure a signal. This is a fairly spooky one. So here now the gravitational wave data is on the top, and there's a sensor, a microphone at the bottom. These glitches used to come in storms, and they'd go on for seconds or minutes at a time. We'd hear nothing for a couple of hours, and then it would come back, and it sounded like somebody's at the door knocking. And this is happening 4 kilometers away. There's nobody down there. And we could not figure that out until somebody saw the culprit fly away. These are these very clever ravens. So this is in our desert sites, and the clever ravens had learned that to get a drink, they could come and peck at the ice covering the liquid nitrogen feeds, which is what we use to keep our vacuum system at an ultra-high vacuum. And this is a very kind graduate student who's doing a simulation of a raven to reproduce the noise. And indeed, we were able to totally mitigate this with a little bit of mesh wire around it. The ravens are all fine. The Columbia River's right there, so we didn't deprive any ravens of any crucial water. I think they just really liked it cold. But I want to emphasize before we close out with a look at the future that this is one of the places where you can get very heartening international news. There are thousands of us, 3,000 in all, if you work across Lago Virgo and Cagra, all working together on the engineering, the data analysis, the astrophysical interpretation, many, many students working across borders. So that's been a real pleasure and a joy to be able to work with this team and watch these results come out, especially in the face of recent news. And I will close with a look at what we may learn in the coming years. So Cosmic Explorer is a gravitational wave detector, not on a 4-kilometer scale, but on a 40-kilometer scale. So on the size of the distance between cities. And if we were to build it with largely roughly exactly the same technology, here's what we would see. So we're here, so where it says a redshift of 1, so that's present day. So we're sort of looking back in time and further away this way. This yellow dashed line, this is the furthest away that we've seen with gravitational waves so far. The green dashed line is about the best we think we could do. So as a cosmologist or astronomers would say, about a redshift of 2, measured in how far light has stretched by the time that it gets to you. If we were to build Cosmic Explorer, we would see absolutely everything all the way out to the dawn of cosmic time before we think the first stars formed. So this would be a big investment in the infrastructure to build these, but the gain that we would get scientifically is tremendous. Any evidence of primordial black holes and also the full evolutionary history of the universe through these mergers. And we'd also be able to resolve this Hubble tension. So this tension between the measurement of how fast the universe is expanding, depending on if you're looking in the local universe or the distant universe. Here we would get it as a function of redshift. And then I'll also mention the space mission LISA. So this is the Laser Interferometer Space Antenna. And instead of a detector on the scale of cities, here's a detector on the scale of a large part of our solar system. So the optimal thing you can do for gravitational wave signal strength is to build an L, 2 orthogonal directions, but that only works well if you've got a network. If you want to have full coverage of the whole sky, you've got to build a triangle. So this limits your peak sensitivity a little bit, but it means you have no dead spots. So LISA will be a triangle of 3 spacecraft that's going to follow behind the Earth and roughly about 20 degrees behind, orbiting around in a cartwheel. And it's going to have a 2.5 million kilometer baseline. And this is going to allow us to sense supermassive black holes orbiting around each other and merging, swallowing things. So we'll be able to get these really, really deep gravity well tests of general relativity. So we'll also be able, particularly with LISA, to do multi-messenger astronomy with light and gravitational waves for galaxy mergers and really get this more complete evolutionary history. And then I would say that LISA is sort of like optical compared to ground-based like LIGO's gamma ray. So ground-based is the highest frequency, and in order to see these different sources at different frequencies, you really need different instrumentation, which brings us to the lowest. So suitably, the radio analogy here, which is pulsar timing. So here, instead of a detector on the scale of the solar system, now we have a detector that's on the scale of a large part of our local galaxy. So here the idea is that you're using this network of pulsars. So these are the same neutron stars that we heard of before, but these particular neutron stars have very strong magnetic fields, and they're spinning such that you get the signal, this lighthouse beam that's extremely precise as a clock. And you can look for these correlated differences in the time of arrival of those pulses to watch space-time breathe with these very, very low frequency gravitational waves of supermassive black holes slowly orbiting each other. So this is a tremendous experiment that's just released a first hint of a first signal. So that's really, really exciting. It's also something that British Columbia is deeply involved with. So the International Radio Pulsar Timing Effort, of course, lost the Arecibo Observatory and the Chime Observatory, which is very close to our sister campus, and the Okanagan has really stepped up to fill this role and allow us to take much, much better measurements. I say us very generously here. So we have a strong group doing this at UBC that doesn't include my team, but we're really big fans. So I will leave you here. So this is an analogy. This is our very, very first gravitational wave detection and the first sketch of Saturn by Galileo with a telescope. And comparably 6 years later, we had about a couple dozen detections from gravitational waves. Here for Saturn, we're starting to see that there are rings. And I invite you to imagine where we're going to be on the order of hundreds of years from now. So I think the future is very, very bright. And thank you very much. I'm really happy to answer any questions.